Good evening, everybody, and welcome to the Sigma meeting for January 2024. First of all, I'd like to say Happy New Year to you all. And for those of you who don't know me, my name's Pete Sherman, and I'm the chairman of Sigma, and I'll be your MC for the evening. Just going to say sorry for the late start, but we had a little bit of trouble with Andy's microphone earlier on. Andy, do you want to just try and say something, see if we can hear you now? No, there's still a problem there. Okay, so we're going to mess around a little bit tonight and change a few things around. Right, so to start off with, I'd like to, sort of welcome everybody, not just the Sigma members, but also our affiliated club members as well. That would be the Highland Astronomical Society, Aberdeen Astronomical Society, Caithness Astronomical Group, North Ronaldsea, and Dundee as well tonight. I believe we've got joining us. And I'd also like to welcome all the first-time visitors we have tonight. We've got Moira, Peter, Rachel. I think we've got Melvin and Guy and Savets, and also welcome back Chris and Margaret Sharp, who've rejoined Sigma this year as well. So you're all very, very welcome. Right, just before I start, I'm going to hand over to Ray for a moment, who's going to tell you a little bit about the workshops that are coming up in the next few weeks. So Ray, if you're there, if you want to unmute.
Okay. Right. Yeah, just a quick one. It's just to follow up on the various communications that you've had from Pete regarding the up and coming astrophotography workshops. And it's just briefly to say that for those of you who are unsure what to expect, if you didn't make the actual talk, just contact the committee and they'll send you a link so you can look at the talk. Because basically what these workshops are going to be is going into the subjects covered in the talk, but in a lot more detail. So the intention is to start off with just basic sky photography, stars, free software to process star shots, things like Milky Way shots, Aurora, things like that. That would be the first session. The second session would be on imaging planets, solar system objects, and the third one will be on deep sky object astrophotography, which is quite a complicated subject. And it may well be that if you attend these things and we want more, we can always add additional sessions for each of these topics if required. Being that this is a workshop, it's hopeful that everybody will come along and bring their own ideas or things that they think are good practice that work for them and share that with other people coming to these things. So hopefully it will be, everybody will learn something, and hopefully from each other. What I'm going to do is I'm going to send a email or WhatsApp or both message outlining what we can expect in these sessions. And it won't be particularly definitive, but I'll give you an idea of the sort of topics that we're going to cover. Like I say, it's just going into the individual parts of the talk that I gave in November in a lot more detail, because it's impossible to go into any detail in each of these three subjects in 1 hour. So we'll have a lot more time to do that at these sessions. So really, that, as I say, if you're unsure, you're thinking about coming but unsure what to expect, then please just email the committee and we'll send you a link and you can look at you look at the talk and see what the actual sessions are going to be about. So that's really it, and we'll be in touch soon regarding these sessions, and so hope to see as many of you there as possible.
Okay, Ray, thank you very much. That's great. Right, Andy, have we had any luck? No, we haven't had any luck. Right. Right, what we're going to do, right, before we start, we'll turn things around. We'll do the second half first, and then we'll try and get Andy sorted out in the break, unless he gets himself sorted in the meantime. Then we'll start on with his talk. So sorry about this, people, but technical issues, great stuff, isn't it? Right, just a little note on membership. So I know we do lose a few members during in the second half. Well, we won't this time, obviously, but I'm going to do this now anyway. It's been decided in committee that there will be a membership cut-off period for actually paying your subs. In the past, we've sort of left it open a little bit. The reason being people rejoin sometimes in October, but they've still been a member but haven't paid their subs until October. But now with the GDPR regulations, we have to be very, very careful on. Oh, did I hear something then, Andy?
Can you hear me?
I can hear you. Great stuff. Right.
Ah,
If you give me a minute, I'll finish this, then I'll be over to you.
okay.
Okay. So to say the cutoff for your membership renewal, the payment of your memberships money is going to be on the 15th of February. After that time, we will have to take you off of all the email lists and the other groups as well. As I say, it just keeps us right with the GDPR. We've got to be very, very careful with this. Okay, so anyway, on with tonight. So helping me in the background, we've got Rich and Mick, who are the Zoom co-hosts. So if I get anything technical happen, which the way it's going tonight probably will, they'll take over and carry on. Okay. Also in the second half, we've got Mick, who's going to do the Morning Sky at night, and we've got some fantastic astrophotographers photos come in from many members, so I'll be showing those in the second half. Chris, he'll be handling up the Q&As, and I'll explain how you can ask questions in a minute. Okay, so with the Zoom controls, so if you have any questions for our speaker at all, there's a little, because anyone who hasn't used Zoom before, we probably all have by now, but it's been a while. You'll have a toolbar at the bottom and you'll see where it says Q&A. If you click that, you can put a question into the Q&A at any time throughout Andy's talk. And I say, Chris will keep an eye on that, and he will then ask the questions over to Andy at the end of his presentation. We'll ask you not to put your questions into the chat, because the chat can move quite quickly, okay, and the questions will then get lost and won't be asked. The chat is open at the moment and will be open during the break. It will be turned off during the presentations because it's very off-putting when the speaker keeps getting pop-ups coming up on the screen. I say, just in the little note in there, if there's a little up arrow next to the chat, or when you open the box, there's a little arrow, make sure you change it to all attendees and panelists. Otherwise, your chat only comes through to me, Mick, and Chris, and everyone else here as a panelist. Okay. So, I would just ask now, remind all the panelists that they make sure their mobile phones and home telephones are off the hook so they don't ring halfway through Andy's talk, or whenever they're actually doing a talk themselves. So the way it happens tonight, I say we have the main talk from Andy, and then we have the Q&A. We will have a little 10-minute break as well. It just helps us get set up ready for the second half, and we can have a little break ourselves. We've been here about 6:30. So after the break, I'll show you these wonderful members' photos. Mick will give us the Moray Sky at night, and then I'll finish off with a little bit of club news. Okay, so tonight it gives me great pleasure to welcome Andy Green. Andy, I say this is Andy's first time with Sigma, giving us a presentation. And I say he'll be talking about his favourite subject, the Aurora. Andy is fellow of the Royal Astronomical Society, has been actively involved in astronomy and space for over 46 years, becoming interested in astronomy at the age of 7. Right? That's probably the same as me, I would say, Andy. That was a Voyager era, I'm going to guess, as well, was it? Just
moon landings, just after.
Yeah. Okay. He has travelled the world many times to promote astronomy and give presentations and lectures far and wide, talking to varied groups. He was involved in grassroots astronomy for many years, and he has seen astronomy at all levels, from local astronomy society level to public understanding of science and space for professional astronomers. And his particular interest, I say, is the Aurora, and he spent over 11 years researching, observing, and photographing them in Iceland. And he has a degree in geoscience and planetary geology from the University of Sheffield. He is also a freelance space journalist and photographer, and has had articles published in several magazines, both in the UK and USA. As an accomplished photographer, his images have been published in many publications and used online, in addition to many hard copies, publications of books worldwide. So Andy, thank you very much for joining us. And would everyone please give him a warm welcome.
Thank you all very much. Hopefully everybody can hear me now.
Yeah, we can hear you and we can see your
Good.
screens.
Great stuff. So thank you all.
Do you want to just go full screen on that, Andy, so we can get rid of the toolbar?
Is that better?
Okay, over to you.
Yeah, thank you all ever so much for inviting me along to give this presentation about one of my favourite subjects, which of course is the Aurora. And given where you all live, you're in a perfect position up there to be able to see it for yourselves. It's a bit more difficult for me in the UK because I live down in Cambridge, so it's not very often that we ever get to see it. But what I'm going to do tonight is I'm going to try and explain a little bit about what the Aurora is. We're going to talk about some of the people that were involved in explaining what the Aurora was, and then we're going to talk about some of the legends associated with the Aurora, because that can be quite different depending on whereabouts on the Earth you are, and then we're going to talk about a little bit about my experiences of searching for the Aurora in Iceland. If anybody needs any information or any pointers, then please feel free to let your chairman know, and he can send me a message and I can send you some information. So, in search of the goddess of the dawn. Now, any astronomical presentation can get very, very technical very, very quickly. And of course, if we use equations to try and explain things, you'll all be asleep within the first 5 minutes, unless you're into mathematics, of course. So I'm not going to use any more of these equations. I just put that there just to give you an idea. We're going to look at lots of pictures and lots of animations and things like that instead, and hopefully that'll captivate you and keep your interest. Now, the Aurora then, Aurora was the goddess of the dawn to the Romans, and Aurora is a Latin word meaning dawn, and of course Boreas means pertaining to the north. So the Aurora Borealis is the northern dawn, and the Aurora Australis is the southern dawn, and they're pretty much a mirror image of each other because of the way the Earth's magnetic field is aligned. So what we see in the north, we can say that somewhere down in Antarctica there could be a very similar display going on, and I'll show you a picture of that a little bit later too. So Aurora, Latin for dawn, Boreas towards the north. So where can we see these lights? Well, generally we're limited to Scandinavia, northern Europe, Siberia, Canada, northern North America and Alaska. In the south, mainly Antarctica, but sometimes in South America, southern Australia, Tasmania and New Zealand. But of course, if the sun is very active, as we've seen in recent months, then the activity is heightened and that visibility comes further south, and we've been seeing Aurora through Scotland and into northern England very recently as well. So we can see them in lots of places around the world, but the Aurora Borealis is of course better known because it's seen in a greater populated area. In the southern hemisphere, down in Antarctica, there's only generally the scientists and the penguins down there to see it, not many humans at all, whereas in the north, we're covering a greater populated area of visibility. The key to the Aurora really is our star, the sun, and I'm sure some of you, when you get the chance, have observed the sun in hydrogen alpha and seen the prominences and the flares. Well, our star, the sun, luckily for us, is an ordinary star. It's going to last for at least another 5 billion years, as far as we can tell. It's not big enough to blow itself to pieces as some stars do. So it's going to merrily go on its way for quite some time. And it's the sun that's the key to the Aurora. Without the sun, there would not be any auroral displays on Earth. You can see from this picture the size of the Earth. We could fit about 1,300,000 planet Earths inside our star. So the sun compared to us as a planet is really, really big. The sun emits energy at the rate of about 4 million tons every single second. And if you imagine if we could harness that power in 1 single second, there's enough energy released that would keep the whole of Western Europe in electricity for the next sort of 200,000 years. And, that would come in quite handy, especially with the cost of energy at the moment. Then, it'd be great if we could harness that power. But the sun's losing 4 million tons every single second, but there's enough energy and hydrogen there to keep it going for a good few billion years yet. Now, the sun, of course, is a dynamic body, even though we don't realize it. It is. We see the sun in the daytime, and it gives us the light, and sometimes we do take it for granted as to what it actually is. And inside the sun, what's going on is all the energy is down here in the core, and in the core of our star, the temperature down there is about 15 million degrees Celsius. It's pretty hot, but over a period of time, that energy is able to rise up through the sun. It rises up through the shell and eventually reaches the outer part, which is what we call the photosphere, this sphere of light. And by that time, the temperature has dropped to about 6,000 degrees. So from 15 million in the core to 6,000 on the photosphere, and that means it's a good job we're living 150 million kilometers away from it, or 93 million miles, because any nearer, of course, the Earth would be too hot and we wouldn't be in this thing called the Goldilocks zone. But we reckon it takes about 1 million years for the energy from the core, from this nuclear fusion, to rise up through the shell before it gets to the photosphere. Now, inside the sun at the moment is in a state of balance. And what we know is that the nuclear pressure in the core, this thermal pressure, is pushing outwards in the sun, and gravity is counteracting that thermal pressure by pushing backwards inwards. So the sun, we can say at the moment, is in a state of hydrostatic equilibrium. And all that means is that it's going to merrily go on its way, burning hydrogen for the next few billion years. It's not going to get significantly bigger just yet until that hydrogen runs out, when the sun will expand and become a red giant star, but then it will shrink again over another billion years or so, and then it'll become a white dwarf. But while ever there's hydrostatic equilibrium, the sun will continue to turn hydrogen into helium, and there'll be activity of solar flares and solar prominences, which again, I say, is the key to the aurora. But the problem for us in a few billion years' time, of course, is that the Earth will eventually die because the sun will get so big it will come towards the Earth and our orbit, and all the oceans, the lakes and the rivers will disappear, and of course the Earth will become too hot to live on. Hopefully by then, people will have devised a way of getting us to the planet Mars, and maybe we'll be living on Mars by this time, or even further beyond that. But certainly the Earth is not going to exist in a few billion years. In fact, Earth will disappear inside the sun, as will Mercury and Venus. So nothing living there will remain. We'll just be like a burnt crisp back in the future. Now, the sun also spins around, much like the Earth and the other planets do. But the sun is a bit weirder, because the sun isn't a solid, it's this churning gas. And this is what we call, on the left-hand side of this picture, is what we call granulation. And the best analogy I think of how the sun works is to just imagine a kettle. And imagine that the element in the bottom that warms the water up, that's the nuclear reactor in the core. And as the water gets hot, that water rises as it heats, and then as it cools at the top, it sinks a little bit and then goes around in this sort of direction. So the sun essentially is doing that all the time. So there's no physical hard surface there. And what that means is that the sun, unlike the Earth, has got this thing called differential rotation. And what that means is there's a 10-day difference in rotation speed between the equatorial region of our star and the polar regions. And because of this differential rotation, the magnetic field of the sun moves quicker in the central part of the sun. So it's moving faster there. And what that does is it twists and distorts the sun's magnetic field. And in this area of the equator where it's moving very quick compared to the poles, that 10-day difference is when we get these magnetic field lines occurring, and this is where we get the sunspots that we've all heard of before. Now, sunspots themselves, imagine a horseshoe magnet, and you've pretty much got yourself a sunspot. And in these areas, the magnetism is so much greater than it is everywhere else in the sun, because the sun's magnetic field is twisted in those areas. So imagine a sunspot with a north and a south component as a horseshoe magnet, and the thing about the sunspots is that they're also a little bit cooler. They're about 4,000 degrees Celsius. So the magnetic field in those regions of those sunspots where that horseshoe magnet is are thousands of times stronger. So we always get a sunspot pair where one component is north, one component is south, and the magnetic field lines between them generally rise up from the sun's photosphere and then arch around, and they're captured by the opposite pole at the other side of the sunspot. From observations, of course, what we have seen is that these sunspots go in a cycle, and this cycle is 11 years from solar minimum, where you can see on the right hand side there's not much activity there, coming into solar maximum, which is 11 years later. And we're just beyond that now, and we're heading back down towards solar minimum in another 11 years. So now is a really good time to be going out and having a look at the aurora. So throughout history, astronomical history that is, people have measured and monitored how many sunspots there are around on the sun's disk. And this is a classic diagram that is in pretty much every sort of physics textbook about astrophysics, called the butterfly diagram. And what it does is the middle part, PQ, is the equatorial part of the sun, and you can see the sunspots generally go between 30 degrees south, 30 degrees north, which is where that the sun is rotating the quickest, and that's where they are. So through observations, we know on the left hand side is a real image of a sunspot. The Earth would fit inside that no problem at all. So the umbra is the inner region where it's really dark, and then the penumbra is the outer region. But of course, like in all science, things don't always go to plan. There's always a sort of a spanner in the works, or something happens that we just don't seem to be able to quite explain. And one unusual event that happened was this period called the Maunder minimum. And between 1645 and 1715, the people observing the sun and making notes of sunspot numbers rarely ever saw sunspots during that time. And what they realized was that not only were they not seeing sunspots, but the incidence of aurora observations were very, very, very low. So they said, well, there's got to be a link perhaps between these sunspots and sun's activity and these lights that we see in the polar regions. But the Maunder minimum also is where people had this idea of climate change and things, the climate changing, it getting cooler, because it just so happened that during the Maunder minimum was when rivers like the River Thames in London, the River Seine in Paris, and the Rhine in Germany, they were freezing over, and they were having these fairs on the ice. So people said, well, if the sun's not very active and there's not much energy coming to the Earth in the form of solar flares, then the Earth is going to be cooler. So the whole idea of climate change came about way back in the 1600s. Now, when there is a solar flare, what happens is, instead of being captured by the two poles of the sunspot, the energy can escape the surface because the sunspot's magnetic field is not strong enough to hold on to it. And that's when you'll hear on the aurora forecast, and they'll say there's been a CME, a coronal mass ejection. And that means there's been a big solar flare that is able to break free from the sun in the form of protons and electrons that occur near these sunspots, and they're emitted into space as the solar wind. This is a a solar flare, big one a few years ago now, and you can see how big that was compared to the Earth. And the sun is sending these things out in every direction. But for Aurora, of course, we need it to be coming towards planet Earth. And when that solar wind does come from the sun and it's directly in a line with us, then the protons and the electrons are captured by the Earth's magnetic field, and they're channeled then to the northern and southern polar regions where the magnetic field is the weakest. Of course, the Earth's magnetic field is slightly different from the geographical pole, which is why if you were directly at the North Pole, perhaps the area of activity would be further south and you wouldn't necessarily see northern lights right at the pole. But if you're on the magnetic north, then you would. And I don't know whether you remember, I certainly do, when I was a teenager in school doing physics, we did this experiment whereby we got a bar magnet with a north and a south, covered it in a piece of paper and sprinkled iron filings on it, and lo and behold, we got a perfect picture of the Earth's magnetic field. So you can see in the middle it's wider, whereas at the poles the lines come directly into the north and south part of the magnet, and the Earth's magnetic field actually works in a very similar way. One thing about the geographical pole of the Earth is that will stay where it is all the time. The problem with the Earth and having a molten core of iron is that the magnetic field of the Earth can move around a little bit. And we know that in some of the sagas, for instance, these stories written in the Middle Ages in Iceland do not mention Aurora. And it could well be either that they believe that everybody saw it so they didn't think it was worth mentioning, or that the magnetic pole was too far north and the activity, what we call the auroral oval, would have been a little bit too further north for them to see it. So it does shift around, and we can see here that the south magnetic pole and the north magnetic pole do that as well. And again, that's to do with the internal molten iron core of the Earth that shifts around. Over the years from 600 AD to 2000, you can see where the magnetic field has moved around. And the idea here is that this orange and yellow circle that's moving as well is the area of activity where we would see auroral displays. So it does shift around quite a bit. Now, this solar wind then. So we said that when a coronal mass ejection, a solar flare, or prominence is released from the photosphere of the sun between the sunspots, they can travel pretty quick, anywhere between 300 and 2,000 kilometers an hour. And generally, to travel the 150 million kilometers towards the Earth, they generally take between 2 and 4 days to reach us. And that's why you'll get an alert on your Aurora app that will say, right, in the next couple of days, the chances are you're going to see it. Because what we have now, satellites, their total job is to monitor the sun and its energy and its emissions of these flares. And when they see a flare, they can tell us, right, in 2 or 4 days' time, we're going to be hit by these particles, this solar wind from the sun, and that's going to cause a display of aurora. So the bigger the coronal mass ejection, the more protons and electrons there are in the Earth's magnetic field, and over a greater area we will see it. So it generally takes 2 to 4 days to get to us, and this is an animation that hopefully you can see. We've got the sun on the right-hand side. You'll see a big flare's erupted, and there's the solar wind. And if you look at this wheel on the left-hand side, you'll see as it comes past the Earth that the solar wind, the density of that increases. And as soon as it starts getting past us, then you can see it goes right into the red part of that that indicator there. And that means that, you know, we've been hit by a big batch of solar wind. So let's go and have a look for some aurora. But again, things don't always go to plan. And I'm sure you've come across this event in 1859 called the Carrington event. And Richard Carrington and Richard Hodgson, two astronomers, they were both observing the sun and they independently saw this solar flare, and they knew because they'd seen this flash that it was Earth facing and coming towards us. Well, this flare turned out to be so powerful that instead of taking 2 or 4 days to get to the Earth, it took 17.5 hours. And there was so much activity in the Earth's ionosphere from this solar flare that they were seeing aurora down in the Caribbean and Cuba and places like Hawaii. So they were seeing it much, much further south than anybody had ever seen it before. So we used to think that the Carrington event was the most powerful solar flare that had ever been observed. That was until a few years ago, because somebody was looking in a library in Japan, and they came across this observation of a brilliant display of aurora in 1770, so way before the Carrington event. And by looking at the description and the diagram and where Tokyo is and how far south it is, they reckoned that this was anywhere between 5 and 10% bigger an event than the Carrington event was. So the Japanese in Kyoto in 1770 were given this display of bright red aurora, again, that was probably the most powerful solar flare ever emitted. We didn't know about this until a few years ago. Another unusual event in America happened a good few years ago now, in the 1920s, and this one is where a solar flare was affecting the telegraph lines in America, knowing that these telegraph wires of the telephone calls and things like that, there was no reason to have any power because there was enough power in the ionosphere because of this solar flare. They were still being able to communicate and telegraph between places, and just by the energy from the solar flare. So that one happened in America in the 1920s, a similar event. Not as powerful as the Carrington or the Japanese one, but certainly enough to play tricks with the communications. Where do we see the aurora in altitude? Hopefully, if you have been lucky enough to see the aurora, it sometimes feels as if you can just reach out and touch it. Because it's so bright. But the lower edge of most auroral displays is around 95 to 110 kilometers in altitude, so 10 times higher than a jet's flying. Sometimes it goes up a little bit higher than that. And when the space shuttle program was on, and it was actually seeing aurora in orbit as well. So the space shuttle was an ideal platform whereby to see these auroral displays. And the International Space Station now is perfectly placed. And one of the things that the astronauts like to do more than anything else is to go down to the area with the biggest windows, this module called cupola, and they watch the aurora australis primarily going underneath them in space from the International Space Station. But the space shuttle, before it retired in 2011, they observed the aurora up there as well. So it's at an high altitude, but why do we get the colours? I'm sure people sometimes have convinced themselves that they've not actually seen the aurora when they actually have, because I've seen displays that look very, very faint, and they look almost white in colour, like a very faint white. But that's generally because the conditions are not ideal. But the colours themselves, the reason we get them is taking you back to school again. In the atmosphere, we have two different types of oxygen. We have the molecular oxygen, which me and you breathe, which is the O2 oxygen in the atmosphere. We have atomic oxygen, which is higher up in the ionosphere, and then we get atomic nitrogen. And casting your minds back, you'll know that the protons and neutrons are in the nucleus of the atoms, and orbiting around that is a specific number of electrons. And what happens with these solar flares and the solar wind is, because the solar wind has a lot of electrons in it, as soon as it comes down the magnetic field lines, it begins to interact with the atomic oxygen, the molecular oxygen, and the nitrogen in the ionosphere. And what happens is they gain an electron. So in the case of atomic nitrogen, it's got 7 electrons. Atomic nitrogen suddenly gets 8 electrons. Atomic oxygen gets 9 electrons. And the molecular oxygen, again, doubles up on that and gets an extra electron too. When these gases get this extra electron, they do not like having it. So the way they get rid of that extra electron is to get rid of it by emitting a photon of light. And this photon of light, depending where it's emitted, if it's emitted in the with atomic oxygen, it takes up to 2 minutes for this electron to be emitted from the atom, and that means it gives it off in this area of 630 nanometers, and that means that color is red, which is harder for us to see on the Earth. Our eyes seem to be better adapted to the molecular oxygen, which is at 557, which is the green bit of the spectrum. So we see green as a better color in our displays, and then the nitrogen is even lower than that, and that gives off this magenta or this pinky color. So the way it gives off this electron, the technical term for it is called quenching. So when the electron is quenched, the photon of light it gives off, depending whether it's from the atomic oxygen or the molecular oxygen, then that dictates what color that we see. And it can be a mixture of all of them as well. So green is the dominant color of the aurora, but we have to be very, very careful, because the internet, of course, and social media. This is an image from 2017. It's been doing the rounds on the internet recently as well. And somebody was saying that they'd seen some very strange aurora in Finland. And you can see these white curtains of light up there in the heavens. And everybody went, "Oh, this is amazing." And I just looked at this and thought, well, I've seen displays of aurora like this, and none of them have ever been white. Something's just not right. And I was right, because it turned out to be a group of students with these light ones playing tricks with everybody. And in fact, you can still see the cables in both pictures where they've done the light drawing with these lights. So we do have to be careful. So I thought, well, white aurora, never seen anything like it. And then I saw a white aurora. And at first, people, when we documented this, and more people have seen it since, they said it was a proton arc aurora. The problem with a proton arc aurora is that protons wouldn't be visible at this sort of wavelength. So what the scientists called it was a Steve. And Steve was just another name for we haven't got a clue what it is. That was until we came up with this thing, strong thermal emission velocity enhancement. And the European Space Agency actually have this satellite called SWARM. And it's European Space Agency, it's monitoring the magnetic field of the Earth. And SWARM observed a Steve and worked out that it was actually this 16-mile wide ribbon of hot plasma at an altitude of 280 miles, which is way above where the normal aurora is displayed at, and it's very, very hot, and because of that, it gives off this emission of sort of white light, and it's in a perpendicular direction to the normal aurora. So this thing tends to go east to west rather than north or south. But again, luckily, with the advent of technology and satellites, that we could actually do that. They were thinking about launching what we call a sounding rocket into one of these things, but 280 miles is higher than the International Space Station, so that would have been pretty difficult to do. But SWARM, this satellite, actually observed this Steve and told us what it was. Of course, we get different forms of aurora. We get patches, which is where we might just see a faint patch of green in the sky. Everybody wants to see the curtains, which are they're dancing around the magnetic field lines. We can get a band or an arc, or we can get aurora directly above our heads, which is called a corona, which is like a big cavern coming down towards us. Or we get the veils, rayed bands and arcs, or rays. And sometimes the aurora can last for just a few seconds. Sometimes it can last for hours and hours and hours. It's all to do with how dense that solar wind is that's hitting the atmosphere and the magnetic field of the Earth. Who was it that actually had an idea what it was? Well, I'm sure you'll remember this guy, Edmund Halley, he of cometary fame. And Halley had never actually observed the aurora directly himself, but he'd seen reports about it. You know, he was around not too long before the Maunder Minimum and things like that. But he'd heard reports about these lights, and it was him that he deduced that he reckoned it was particles moving along the magnetic field lines of the Earth. So way back in 1716, Edmund Halley was thinking about the magnetic field of the Earth, even though he'd never seen the aurora. Then two other famous astronomers came along. I'm sure you've all heard of Galileo, one of the first telescopic astronomers discovering moons of Jupiter and the rings of Saturn, and this guy called Pierre Gassendi. And in the 1600s, they both observed these weird green lights in the sky, and we're told it was one of these two that coined the phrase Aurora Borealis. Now, of course, when you were as far down in Italy as Galileo was, that really tells us something way back in the 1600s, that if they were observing aurora back then, that there obviously wasn't much light pollution around then, and they could see the sky really, really well. But Galileo or Gassendi were the people that coined the Aurora Borealis. My hero in this story, though, is this Norwegian guy. And this Norwegian, he was called Christian Birkeland. And Christian Birkeland, he was a bit of an eccentric character, if you could say. He was a professor at the university in Oslo, as it was then, or the University of Christiania back then. And what he did, he was a bit of an inventor. He invented a way of separating potassium from fertilizer. He invented this thing, the electromagnetic cannon, which is whereby a magnetic field is induced and then a projectile comes out from the coils. And it was when he was displaying this particular type of apparatus to this guy, King Oscar of Norway and Sweden, at the turn of the century, that Birkeland actually nearly killed the king, because somebody put the projectile into the magnetic cannon a little bit too early, and it shot across the laboratory and nearly killed the king. And the king gave Birkeland the 5,000 kroner he needed there and then, just to get rid of him on one of his expeditions, because he didn't want to be killed by anything that Birkeland had invented again. So with this money that the king had given Birkeland, he went on several expeditions into the Arctic. And what they did is they measured the magnetic field intensity and compared that to what was visible in the nighttime sky. So what they realized was, by experimenting, that when the magnetic field was active, because there was lots of solar wind there, they could see the aurora really well. So Birkeland said, well, it's got to be the energy from the sun in the form of particles, of protons and electrons, that interact with the Earth's magnetic field, interact with the oxygen, and give off these lights. So what, like any good scientist would do, Birkeland headed off back to Oslo, and he wrote a paper about his experimentations and the expeditions, and he invented this thing called a terrella. And a terrella was essentially just a box, and about 3 feet square, and inside that box was a spherical magnet that represented the Earth, and then it was magnetized, and then all the air was drawn out of this terrella, this box. And what he did then is he introduced some electrons into that box, and lo and behold, the electrons were attracted to the north and south pole of the magnet and gave off this glow, just like the aurora that he'd seen. So the more intense the amount of electrons there were, the brighter it was. The less electrons there were, the dimmer it was. So he knew he found the idea as to why the aurora was and the way it behaved. So he wrote this paper, and he submitted this paper to the Royal Society in London. And he thought, well, I'm going to send it to the people that really know about these things. And the trouble was, is at the time in the Royal Society was this gentleman, Sidney Chapman, and he had ridiculed Birkeland for being a bit of an eccentric and a bit of a stupid scientist, a bit of a nobody, because nobody had really heard of him outside Norway. So it was this guy Sidney Chapman who'd worked at all these universities and observatory, the Greenwich Observatory, and he'd argued that these currents that had been coming across space and interacting with the magnetic field, they couldn't cross a vacuum. Therefore, the currents that were causing the aurora had to be generated by the Earth and not coming from the sun. So Birkeland's theory was, sort of disputed and ridiculed by not just Chapman but others there as well. And it was only when Birkeland died that Sidney Chapman had to confer that in fact Birkeland had been right all along, and it was these currents, these streams of solar wind that passed down these lines called Birkeland current lines and then interact, and Birkeland had been right. So it's just a shame that a scientist was recognized in his death rather than he should have been recognized when he was alive, and it seems to me that happens quite a bit. But Sidney Chapman eventually ceded to Birkeland as being the correct one. Birkeland died in very suspicious circumstances in Japan. They reckoned that because he was up all the time at night time doing his observations, that he couldn't sleep very well in the daytime. So they reckon he was given some barbiturate to put him to sleep, and he was meant to have taken 0.37 milligrams of this sleeping pill, and he took 37 milligrams of it and he never woke up again. So some people reckon he was murdered, but that's another story. So ridiculed, but he was correct. Then, of course, as science moves on, we get this thing called the auroral oval, and this is this area of activity that shifts when the Earth's magnetic field shifts. And we talked a little bit about that earlier. The greater the activity, then the wider the auroral oval is, and then we can see the aurora in a wider group of places. And this is the image I wanted to show you about the Arctic and the Antarctic. These two images were taken at exactly the same time, and of course we can do that because the Earth's tilted over by 23.5 degrees, so part of Antarctica is in darkness while the northern pole is in darkness, and they are of similar form because the magnetic field works in a very similar way north and south. But again, don't believe everything that you read online about these auroral predictions, because even they can be wrong. The University of Central Lancaster, they usually send out aurora alerts, and they sent one aurora alert out which indicated that there'd been this massive spike in activity in the ionosphere, and that everybody should go out and have a look for this aurora. And then it was a bit later on that day that they had to rescind that, and what had happened is somebody had been using a lawnmower which was local to the Lancaster monitoring site, so it wasn't a big event at all. It was somebody interfering by cutting their grass. So you have to be very, very careful. And one of the other things we have to be careful about is this thing that you will have come across, which is called the KP index. And K is a German word, Kennziffer, which means significant digit, and P means planetary. So the idea being that Julius Bartels, the University of Göttingen in 1938, before the Second World War, said, right, if there's a 0 KP index, then there's not going to be any aurora. If it's 9, then that's the highest level of auroral activity that there can be, and the sky will be on fire. What I've learned over the years is to ignore every app that I've ever had to do with the aurora, because there's been times when I've been out when it's been KP 0 and I've seen brilliant aurora. I've been out when it's been 7 and 8 and I've not seen a thing, because what it is, it's an average measure. And it's averaged over about 11 different stations across the globe over 3 hours. And because the Earth is rotating very quickly, in 3 hours, by the time you've got the aurora alert, we could have moved out of the area of activity. So we might not see it. So what we do in other places, of course, is we can monitor the aurora locally. And in Iceland, there's a place called the Leavoga Observatory, where their aurora indicator is updated every 10 minutes, which is a bit better at predicting whether there's going to be activity. But everybody bases everything on the KP index, but don't always believe it, is what I'm trying to say. Go outside if it's clear and there's been a flare. You never know, you might see it. Do we get aurora from space? Well, we certainly do. We saw that the space shuttle and the astronauts on board that would have seen the aurora. This is Cupola on the International Space Station, which has got the biggest windows, and they regularly see amazing displays of aurora. I mean, it must be amazing to see something as bright as that as you're orbiting around. And because of the way the orbits are with the ISS, they tend to observe the aurora australis more than they do the borealis, because just the way the orbit works. But amazing images from the station of aurora. Absolutely incredible. You can see the red here is easier for them to see because they're higher up above the red, whereas on Earth, of course, if we see the green better, we're trying to see the red through the green, so it's a bit harder for us to see. But what an amazing vantage point to see displays like this. There's one of the Soyuz capsules that brings the astronauts and cosmonauts backwards and forwards. So yeah, so we see them from the International Space Station. Mars Express Orbiter indicated that there could be aurora on Mars. So even though the Martian atmosphere is very, very thin, it did indicate that the magnetic field intensity was higher in certain parts of the planet. So if an astronaut had been there, possibly they might have seen some activity in Mars's thin atmosphere at night. Certainly on Jupiter, being the biggest planet, primarily hydrogen and helium, that creates its own auroral systems, which this one was observed by Hubble. And certainly the next planet out, of course, is my favorite planet, Saturn, and you can see the blue aurora at the bottom of the planet here. So certainly other planets do get auroral displays, and no doubt auroral displays are visible on lots of these extrasolar planets too. That's quite an impressive one on Saturn. I wish I could see something like that through a telescope. That'd be pretty impressive. So tips for aurora hunting from me: look out and see if there's been a geomagnetic storm. Do not necessarily believe what the KP index says unless you know that it's been updated within a certain time frame and not every 3 hours. And there are many apps available, so have a few of them just to give you the best chance. But when the activity is increased, go somewhere dark, where you are, you've probably got some really dark places to go and view north, and look north, and the chances are you'll see it. In the UK, of course, it's the weather that really plays havoc with our observing. So we've got to hope that if there is a solar flare, there is an alert, that the weather plays ball and it's clear when that actually hits the Earth's ionosphere and magnetic field. Now, moving on, hopefully I've got enough time. Myths or legends of the aurora. Are they good fortune or is it bad luck? Hesiod in Greece, one of the ancient poets, he mentioned flaming sky dragons in the 8th century BC, and it was him referring to the aurora. Aristotle seen the aurora resembling a shining cloud. He reckoned it was something to do with these supernatural powers or supernatural beasts. And of course, poets, especially in polar regions, Anson compares the lights to a heavenly feast. In Scotland, you may have come across the merry dancers, where if the dancers move quickly, maybe unsettled weather would come, but the aurora would be dancing pretty fast across the sky, gracefully. If they're moving slower, then the aurora would be harder to see. Greeks and Romans believed that if there was an arch associated with some displays, that was the opening of a celestial cave. In England, again, we believe the aurora was the sounds of battle. People reckon they could hear the aurora. I've never heard it myself, but people have. Some people believe, like from this woodcut, that the Earth and the universe was split into different layers. We have where we live at the bottom, then the layer of stars. They reckon the aurora was this layer of candles somewhere above that. In Scandinavian folklore, of course, one of the things they call the aurora is silsblixt, or herring flash, and the idea being that if you're a fisherman, you go where the bright aurora is, and that's where the light's being reflected off the shoals of herring, so that's where the best catch would be. Some people believe it's the glaciers that absorb the solar radiation, and then they shine that back into the sky at night time. And in Iceland, there are plenty of glaciers, so that could happen. Or it could be two swans deciding instead of flying south for winter, these two fly north and they get stuck in the ice, and it's their wings flapping around that are causing these sparks to cause these weird lights in the sky. And of course, in Norse mythology, the Valkyries, the ladies that went and collected the dead, and they took them across the bridge to Valhalla, where they went and lived in eternity. So it could be the spears and the shields reflecting the light from the Valkyries. In fact, another name for the aurora is Bifrost, or bridge of light, again, which the Norse gods used to find their way to Valhalla as well. So even if you didn't go with a Valkyrie, you would have gone over this bridge. In Finland, the aurora is called Ravonchilet, or another name for the Arctic fox, and the idea being that as the Arctic fox runs across the snow and ice, it's their sparks given off by their fur as they run along, which gives off the lights, which is quite a nice one. In China and Japan, they believe that if you make love under the northern lights, then your son or daughter, when they're born, will be quite prosperous and blessed with good luck. When it's -30 outside, that's a bit cold to be doing things like that, I think. But I did know a guide in Iceland who used to take a mattress in the back of the bus just in case somebody wanted to do that. Of course, the Eskimos see the aurora a lot. They reckon it's a game of football played by the Inuit with a tusk of a walrus skull with its tusks, and the idea being to kick the skull of the walrus, and when the tusks hit the ice, that gives off the lights. This one not to be recommended. The Inuit in Alaska, they feared the aurora, and they hid their children away from its awesome powers. But the way they protected themselves was to throw dog poo and urine at the lights. So I guess if you've got a dog sled, you've got plenty of dogs to be able to do that kind of thing, but not to be recommended. Koenigsspel is one for the flat earthers, because they believe the earth was flat and it was the lights from fires surrounding the flat earth that were giving off the aurora. Red aurora, for instance, could be the blood of battle. So if there was a really bright red aurora like the one in Japan in 1770, then perhaps that could have been the harbinger of a calamity on its way. In Sweden, to do with the fruitfulness of the earth, if the lights are shining, then there's going to be abundance of seeds and a rich harvest in the summer. So again, to do with the land. The Lapps, they hid their women from its rays as well to protect them. So they saw the aurora as being quite a dangerous thing. The Copper Eskimos saw the aurora being responsible for good weather and bountiful hunting, much like the fishermen going after the herring flash or the silsblixt. In Russia, this monk called Kravik, he reckoned he heard the aurora telling him to found a monastery. And he said if the aurora told him where to make it and where to build it, then the monastery would flourish and be wealthy. So again, people thinking they'd heard the lights. Some people reckon that if you whisper at the lights, then they'll whisper back. Tribes of dwarves boiling blubber, if you're a Maka Native American Indian. Other Indian tribes in Minnesota and Wisconsin thought it was the torches of friendly giants used in spearfishing, things like that. So you can see there's all these ideas of icebergs crashing in the sea, in the polar seas, giving off the aurora. Maybe that's true. In Iceland, the one that they have is if a pregnant woman should look up at the sky at the northern lights while she's pregnant, then when a child is born, it'll be cross-eyed for life. So yeah, everybody goes around Reykjavik looking for people with cross eyes. In the southern hemisphere, it was Captain Cook who was one of the first to document the Aurora Australis. By having seen the Aurora Borealis, you can see it said here about 10 o'clock, a phenomenon appeared in the heavens in many things resembling the Aurora Borealis, but differing materially in others. It consisted of a dull reddish light reaching a height about 20 degrees above the horizon. And that was one of the first ever observations of the Aurora Australis. So when we were, sailing down to the southern seas. In Australia, the Aboriginal people believe that whistling or singing at the aurora is dangerous, so best not to do that and antagonize the aurora. But here's my note of caution to you all. So we've learnt a bit about what causes the aurora, the solar wind, and the solar flares from the sunspots and the differential rotation. But if you ever go to Iceland, and many Scandinavian countries are very similar, then one thing to try and get your head around is the language. And Icelandic is a language that has not really been influenced by anybody else. So there's only 330,000 people speak Icelandic. And when you look at some of the words, it's for good reason. This is a volcano that some of you might have been trapped in the Maldives or the Seychelles in 2010. So Eyjafjallajökull is the name of this particular volcano, the one that gave all the ash. You'll see recently they've had some new magmatic volcanoes going off. Imagine if you need to get into a taxi in Scandinavian countries and ask to go somewhere. How the hell do you say these words? Because especially in the Icelandic language, they've got all the letters that we in the English language have got rid of, like the A and the E together, the U's and the funny D and things like that. So it is a really tough language to learn. It is certainly not a place to be dyslexic, because you wouldn't stand a chance. The longest word in the Icelandic dictionary is about 50 letters long, and it means the key to the tool shed, which is just incredible. Another thing about when you're aurora hunting is the weather. The weather can change very quickly. There's no such thing as bad weather. It's just bad clothing. So you've got to be prepared. 1 minute it can be like a blizzard like this was, and then 5 minutes later the sun was out and it was blue skies everywhere. So it's best to be well prepared. Of course, driving in foreign countries, we can see why Scandinavians make brilliant rally drivers, because they're used to driving on stuff like this all the time. Studded tyres helps, of course. When I first went to Iceland and I heard in winter cars driving around, it just sounded like bubble wrap being popped all the time, and it was these studded tyres on the tarmac. But what we do when I do a tour, we give everybody these crampons for their shoes. So it's better to use them and better not to fall down, so be prepared. Get yourself a warm suit like this made of down and keep yourself really warm. If you're cold, you tend to be miserable. If you're warm, you tend to be happy. So it's better to be happy. This is my brother from another mother, one of my favourite people in Iceland. Omar is a very good friend of mine. He's a guide who basically every other company in Iceland that does Aurora tours is always ringing Omar for advice as to where to go and see the Aurora. They always ask him, where are you going tonight? And when he's with me, we always tell them somewhere different. We don't want them to be anywhere near where we are, because we know we're going to get to see something. But yeah, use local knowledge and use local people if you can. Beware the Icelandic wolf. There is no wolf in Iceland, by the way. It's just friendly dogs, especially black ones like this one, Bouncy. In the dark, of course, you can't see him. And I was setting my camera up one night, and Bouncy came coming out of the dark and hit me right in the crotch with his head and knocked me over. And the owner of the hotel, Jon, said, "Oh, don't worry, he's friendly." And ever since then, he's just sat by my feet when I've been doing anything. But it was a bit of a shock in the middle of the dark. In Iceland now, you can be prosecuted for driving under the influence of the Aurora. Because, of course, lots of tourists pick up their hire car at the airport. And if it's dark, they're driving along, but instead of concentrating on the road, they're looking out of the window to see if it's clear and see if there's any lights everywhere. So they've now set up this thing where, if you go off the road in your car, you can be prosecuted for being under the influence of the Aurora. So be careful. This is me in Aurora Ninja mode. Again, just make sure you're nice and warm. You can buy these pants in Iceland for the men with the extra bit to keep you warm. They come in 2 varieties. This is one variety, or you can have this variety. Bit itchy, I think. And not to be left out, if there's any ladies watching the presentation, you can buy something for ladies as well that does a very similar job. But modern synthetic wear is much better. Now, my last word of caution is this. When you go outside, make sure you've got a way of getting back into wherever it is you're staying. This door, which you can see in the background here, was open at the time. But an hour later, the hotel owner, Jon, who's a very good friend of mine, he decided he was going to bed. And the door shut, and I heard it click. And by this time, all the lights had been turned off. So I was outside in a blizzard, in the dark. But I remember that if I was to shimmy my way down the wall where those lights were off now, just round the back of the hotel is a hot tub. So at least I could have died in the warm, having been broiled to death for 6 hours, perhaps. But I'd got visions of my group waking up in the morning and me looking like this, like Jack in The Shining, having been frozen to the spot, having been locked out of the hotel at night time. So that's the end of the presentation. I hope you've enjoyed it. I hope you've been able to follow it. And if there's any questions, we can do some questions. Thank you all very much.
Andy. That was great, Andy. Thank you so very much. I'll just mention, you were saying about apps. I think one of my favorite apps is the Glendale app. You've heard of that one?
Right, yeah.
It's actually people, you can go onto it, and if they're seeing the Aurora, they will put it on there, and you actually get alerts, that real alerts from real people, not just data.
Right.
Yeah,
that's the better one.
It's a good one to look at. It's actually a web page, but they call it the Glendale app, so one to look at. Yeah. Okay then, Chris, if you're there, we will go over for the Q&A.
Yes. Hi, Andy. Thank you very much for that. Thanks for persevering with all the issues that we've had earlier on. And that was absolutely brilliant. Really enjoyed that. There are 3 or 4 questions, and I've got one as well myself. But the first one, sort of following on from what Peter's just said, Rachel's just come in and said, where can I find a good Aurora app that gives notifications of upcoming Auroras, please?
Yeah, the ones that I've got on my phone, and I'm just going to go into it now so I can tell you the correct name for it. I have got Aurora Watch UK, which is a UK-based one, and that one's pretty good. And I'm sure if you go on Apple Store or Google, or you'll find a myriad of different other ones. But the Aurora UK one is the one I use, as well as the one that was mentioned earlier. And give yourself 2 or 3 of them, so you get a better idea as to what's going on. But anything that's with real people or updated quickly are the best ones.
Sweet, thank you very much. So you're talking about the driving under the influence of the Aurora and looking for the Aurora in Iceland. I was fortunate enough to be in Iceland about 20 years ago. There was 4 of us stood outside a nightclub, which coincidentally was called Astro, and we were all staring at this fantastic light show, even in the center of Reykjavik, with all the lights going on, just thinking this is amazing. And talking to one of the Icelandic natives, and he said, you can tell the tourists because they're the only ones that are looking skyward during the winter. So a couple of questions here from Rich. What caused you to become interested in auroras in the first place?
I think what it was, I was invited along to do a recce for a travel company, and they sent me off to Iceland to basically meet a tour company out there. And this tour company they've turned out to be very good colleagues of mine, and I work with them all the time. But that was the thing that set me off, and that was actually almost 16 years ago now. I first went out to Iceland. So it was this trip, but it's like any natural for, people chase eclipses, people like to go to dark skies, but the aurora for me is just mesmerizing when it's active. It just, no two displays are exactly the same. 1 minute it can be very, very slowly moving and hardly seems to be doing anything, then suddenly there's a burst of electrons in the solar wind, and then it can be dancing across the sky. I remember one display, it started at 5:30 in the evening, so everybody missed dinner that night because we were all outside, and I was still outside taking pictures at 7 o'clock the following morning. It was still going on, so
Proper,
it was just
proper dedication.
incredible. So yeah, I mean, what I do on my tours is that I generally send my group to bed, and if there's no activity, and then I'll wake everybody up if something happens. So I'll stay up all night on Aurora watch, because as I say, it's all well and good getting an alert. The best alert I've found is sticking your head out the door, and that's what it's doing.
That's interesting you said that, actually, because whilst we were chatting, John McNichols just put a comment up on the Q&A. Said to check if there is an aurora, you can access the Borrowdale Wind Farm webcam in Shetland. So
yes, you can. I think there's 3 cameras up there. I think one of them faces out towards the sea, and one is down in the harbour. But yeah, so that, if there's aurora visible there, especially for you guys where you are, there's a good chance that you're going to see it a bit further south as well.
Cool. So Svetla's put a question in the Q&A. I'm afraid it could be a bit of a silly question, but here it is. No such thing as a silly question, Svetla. Is the sun, brackets the whole solar system, also orbiting the galaxy?
We are, yeah. We're orbiting at 90 miles a second around our galaxy. The Earth is spinning at almost 900 miles per hour as well. So we're spinning around very fast. We're orbiting very, very fast. We're orbiting the galaxy very, very fast. And we actually wobble on our axis as well. And the wobble takes 26,000 years to make a wobble. It's called precession. And that's the reason the position of the North Star changes. So when the pyramids were being built 5,000 years ago, the North Star was in the constellation of Draco, and that was a star called Thuban. Now we've got Polaris, of course, and in about 8,000 years' time, it'll be Vega that points towards the north, and that's to do with the wobble, the precession.
So basically, we're just a planet full of speed freaks.
We are.
John's just come back and said, the Borrowdale camera faces noise and it's high res. So,
excellent.
So quick question, another question from Rich. What are the indicators of the Carrington events, and are they regular or just random?
Just random, and it's just a matter of, nowadays, because of satellite technology, we've got satellites that are dedicated to pointing towards the sun and observing the sun. That is their job. That's all they do. They do not, take pictures of deep space like James Webb or Hubble or anything. So they're monitoring the sun 24 hours a day, 7 days a week, 365 a year. And if anything is happening on the sun that's Earth facing, one of those satellites will see it, and then that'll tell us. Because the reason they did that was because there's a lot of government agencies like NASA, the US government, and other governments whereby satellites are very, very sensitive to disturbances in their electronics. So what they can do is when if there's a big solar flare that is observed, they can tell them either to turn some instruments off that are delicate or turn the satellite so it's facing away from the incoming storm. So they can do that. And that was one of the reasons they sent these satellites initially. But now, of course, studying the sun all the time, it's brilliant. I mean, looking in the sun in real time and watching the things go off is incredible. But it was all born out of governments protecting their assets, if you like. Because if you've got $1 billion invested in a satellite that's either giving internet in rural areas or it's spying on the Russians or whoever it might be, you want it to be secure and safe.
So that sort of leads me into a question. So Mick put a question earlier on, which was going to lead into my question, but this probably seems like a good time to ask it based on what you've just said, is like the issue with the Parker space probe that I think is supposed to fly closer than 4 million miles away from the sun at the end of
December. It's going to get really close.
And what are the issues potentially with CMEs and the operation of that and the study, because I think it's studying the corona, but so what are the
Yeah.
problems with that?
I reckon what they've decided is with that particular probe is that on its closest approach, as long as they get some data going in, if anything happens to it after, then it doesn't matter, because it's done quite a lot of observations anyway, and as it gets closer to the surface of the sun, it's going to get hot. We know that, but hopefully the shielding is going to be sufficient for it not to be melted. But I'm sure they've got the contingency of, well, we'll have done lots of science by then anyway, so we'll just go for it and see what happens.
And I think this might be the last one, but again, this is from Mick. We know that powerful CME can affect radio transmissions in electronic devices. So with that in mind, does the radiation power which produces these aurora have any effects on anything lower in the atmosphere, i.e. humans? And could it be a possible cause of ill health like cancers, etc.?
Luckily for us down on the ground, we're protected by the Earth's atmosphere and the magnetic field, so we're a lot lower down. One of the things they were really worried about was when the astronauts were in orbit in ISS, or in the 70s when Skylab was up there was a massive solar flare, and because Skylab wasn't shielded, they were worried that this solar flare was going to have an effect on the astronauts. It turned out that it didn't, but we've got to think about the type of radiation as well. So if it's ionizing radiation, that's the really bad stuff. That's going to affect your DNA and things like that. Whereas if it's non-ionizing, we can shield from that. Bits of plastic will shield you from non-ionizing, but ionizing radiation is going to be an issue, not so much for us on the Earth, but maybe when we go to Mars, because Mars doesn't have a proper magnetic field and its atmosphere is very thin. We're going to have to think about having some way of shielding the astronauts that go there in case there is a massive solar flare. But luckily, down on the Earth, we're protected by the majority of the atmosphere and the magnetic field. So it's only higher up that there's a problem.
Sweet. Sorry, a couple more ones. Thank you. Helen sent a link, so if you want to have a look at the Aurora from the Borrowdale Wind Farm, it's shetlandwebcams.com. And then Gordon Mackey, evening Gordon, the intensity of auroral activity seems to depend significantly on the BZ parameter of the solar wind. Can you explain why a negative or southerly BZ is good for generating aurora? That's definitely for somebody with a PhD.
I mean, I could try and do that, but I'd have to go back to all those equations. So, but the best thing to do is to go online and research it online.
There you go. I think that's probably all the questions we have for tonight. So thank you very much. I'll hand you back to Pete.
Thank you all.
Thank you very much, Chris. Just before you go, Andy, Rich wants to have a little word with you.
Andy, thanks very much for that talk. It was absolutely superb, really interesting, properly informative, with some really good slides, mate. So to mark your giving us this talk, we'd like to give you this whiskey tumbler.
Oh, fantastic.
So we'll need your address though, mate, so that we can send it to you. But
I shall make sure it's full of a nice single malt.
Exactly, yeah. But thanks anyway, Andy. That was a really, really nice, good talk. So
brilliant, lovely to meet you all, and
thank you.
Clear skies.
Yeah, it really was good. As I've always said in the past that you can always gauge a good talk by the number of questions you get at the end, and we had a lot of questions there. So we will go for a quick break. Andy, you're quite welcome to stay with us and have a look at the photos afterwards if you wish. Quick 10-minute break, give yourself a chance to get set up for the second half, and we'll be back just then. The chat is now back on, so you can have a chat with everyone in the room if you wanted to as well.
Brilliant.
Okay. Right, hello everybody, and welcome back to the second half of our meeting. As I say, we're going to just go through some of these wonderful members' photographs that have come in over the last few days. I've had to redo this 4 times because the photos just kept coming in. And I've still got a couple more to put in, but we'll hold them over for next month. Okay, so we'll start off with this one. This was Alan Tuff, took a picture of the Aurora, and that was from Elgin up here in Murray. As I say, this was on the 23rd of December at 22:22. Okay, you can see a wonderful image there of the red and the maroon, obviously the green lower down, as Andy was explaining earlier on. And there was another one, a wide angle shot, or a portrait, a landscape shot, I should say, with the trees in the foreground. I would say that's looking out over the Moray Firth. Once again, on the that was on the 1st of December. The 1st and 2nd of December. Now, I'll just point out this: if you're ever reporting Aurora, you'll notice here that he's put the 1st-2nd. The reason for that is, if you put that in, we'll know exactly what night it was on. If you just put the 1st, it could have been the early hour of the morning, or you know, or the evening of the 1st. Also, with the timestamp, that does help as well. I'd say absolutely wonderful image again from Alan. You've probably seen some of Alan Tuff's stuff on the TV. He gets on the Sky at night quite often, and he gets on the news as well, on BBC News. Once again, another one there, wide angle shot with the wonderful rays. And we're very lucky living where we live to be able to see this. Okay, this is another one from Alan. He managed to capture the comet 12P Pons Brooks, and he'd done this with an eye telescope, which is down in Utah in the USA. It's a remote telescope that you can access if you want to pay the fees to do it. And so he's captured that wonderfully. You can see the comet nucleus really well just in here. I'll tell you what, I'll just put this on so I can point a little bit better. Comet nucleus in here. And the tails are just coming out there. Absolutely wonderful shot, Alan. Thank you for sending them in. This one was on Christmas Eve. He sent this in, as he said, that it looked a little bit like a dolphin that was flying over the Moray Firth, one of the Moray dolphins. And then a couple of days after, I had this one come through from Gene Stocks. And I thought, well, that's the dolphin. It's obviously jumped over and it's now heading its way back down into the sea. So this is the Nocretius clouds. They shine really well there. You find them early in the morning, just before sunset, or just before sunset, or just before sunrise, or at night, just after sunset. And it's the sun that's reflecting the sort of ice crystals in the sky, making these shapes. Okay, and so she took that with a Nikon D90, 70 to 300 millimeter lens at f/16, and just a 1/400th of a second exposure. And this is Gene again, the waning gibbous moon. And say once again, that was just with a camera and the 300 millimeter lens. It's amazing what you can actually get with a 300 millimeter lens. The craters are showing it really well there, and my favorite crater there with Tycho. You can see the ejector rays coming out there. This ejector ray actually runs all the way around the moon. And there she is with her image of the Aurora, and that was from Lossiemouth. You can just about see the Pan of Ursa Major there, the Great Bear. So you're definitely looking north, because north's going to be that way. Okay, this is one I took with the club's telescope in the observatory. It's the first chance I've had to actually put my Canon onto it. This was the Dumbbell Nebula. It was about, I didn't put the exposure down. I think I'd done 210-second exposures, 310-second exposures, and then stack them in Registacks, and then, no, sorry, Deep Sky Stacker, and then processed it a little bit in Cyril. Cyril is a free astrophotography software package you can get to bring out the details. So what you've actually got here is a planetary nebula And so you can see the stars in the center, but you can see the gas expanding away from the center of the nebula. And it's quite amazing how many stars you get brought out once you start doing time exposures with a telescope. I'll put that in just to show you how good the Williams Optic telescope that we've got is. And don't forget that is available to all Sigma members once you've done your done a bit of training on it, and the training's not hard. This is another one I've done. Now I took this one with my Dwarf Smart 2 telescope. It's a wonderful item. These are smart telescopes that are coming out nowadays. You can get into astrophotography for just over £500. And I had a dual band filter on there, so that brings out the gaseous nebulosity around here. Let's say this is NGC 7380 in Cepheus, or it's also known as the Wizard Nebula. I took that on the 26th of December. It's another one I took, and I put this one in to show you. This is an actual unprocessed image straight off of the Dwarf Smart Telescope. As you can see, you actually, when you're imaging, you actually get this image building up, and you can see it coming and getting better and better all the time. And the other reason I put it in, because you remember from Ray's talk, he was talking about field rotation. Well, because the my dwarf telescope at the minute is not actually equatorial aligned, and it moves in the sky against the star background, you get this field rotation. You actually see what happens here. So you lose a little bit as the dwarf moves, because it's taken these are all the individual frames that I took. But with a little bit of jiggery pokery, playing around, you can then tease out you can get rid of that, the field rotation problem, and clean up the background a touch as well. I'm not finished doing this one, as I say, because I've messed around with it and I've lost quite a bit of the detail, so I'm going to put that back into Cyril or something else and see if I can get a better image of that. This was another one I'd done. This was of the double cluster in Perseus. Okay, easy way to find this one is just to drop down from the W Cassiopeia. You can see this with your naked eye in the sky. Get your dwarf telescope on it, or any telescope or binoculars onto it, and you get to see this wonderful image of the double cluster. So you have one cluster there, each cluster containing around about 3,000 stars each, I believe. I say that was 294 frames, and with Astro dark subtraction and everything, we could do a talk about that some other time. And I say, once again, processing Cyril. Now this came in from Mark Betson. Once again, he has got a dwarf telescope. I think there's about 6 or 7 of us in the club now who've got one of these dwarf telescopes. And they say this is the Cygnus loop. So you have the gaseous loop all the way around here. And I believe this is the Veil, yeah, that's the Veil Nebula on that side. Very hard to see visually, but photographically, it comes out really, really well. That's fantastic, Mark. Well done for that one. And here's another one. You've probably seen pictures of this all over the place. Let's say you've seen the Hubble pictures of the Horsehead Nebula, which is just here. Once again, you set this with that dwarf telescope. And at the top here, you have the Flame Nebula. And that is the bottom left star of the belt of Orion. So if you want to know where to find that, that's where it is. Okay. Once again, Mark again, he's got the picture of the Orion Nebula, the Great Orion Nebula. And Mark, this is a really, really clean image. I'm really impressed with this one. Absolutely great image. So you can see the nebulosity around there. What this is a star-forming region. And you've got in there what's called the trapezium. So there's a lot more than 4, but the 4 brighter stars you can see in the center there with a telescope is known as the trapezium. And all that gas is collapsing down, creating this. Well, it had collapsed down to sort of create the stars. And this one, unfortunately, the toolbar is covering up the words. Give me a second. I'll get rid of that. Okay, so this is NGC 2174, the Monkey Head Nebula. Yeah, I can't see the monkey head, but maybe I need to have a dram or two to get it to pop out at me. And so once again, he took this with the Dwarf Smart Telescope on the 1st of January. 1st of January, that night was fantastic. That's when I took quite a few images as well. And then we've got his rendition of the Pleiades, M45, or people will probably know it more so as the Seven Sisters. That was on the 5th of December, he took this one. The amount of detail you've got of the gas and sort of nebulosity around those stars, Mark, is fantastic again. Now I showed this to someone today, and they said, "Oh, well, I know that as the flying panel, the Big Dipper." And I said, "No, you're thinking of the wrong thing." Although it's got the shape of the Big Dipper there, the Big Dipper covers an area of the sky, if your arms are outstretched, about 2 hands widths. This covers the area of sky, if your arm was outstretched, of your little pinky finger, or your nail. Okay, so this is the Seven Sisters in Taurus. Easy to see with the naked eye, and you can pick them up and pick these stars up really well just with a pair of binoculars. I'm sure Mick will show you where these are later, perhaps. Okay, and finally we got Ray Palmer, who's going to be giving us the astro imaging workshop soon. I have an idea what date we can do that in, but I need to speak to him first. This is the North American Nebula and Pelican Nebula, and this is in Cygnus. NGC, the NGC stands for National. No, gone. I'll come back to that. New General Catalogue. Okay, it's a catalogue of deep sky objects and sort of nebulous objects you can see in the sky. Okay, say this was taken over 3 hours. This is 3 hours worth of imaging, and then you stack those together. And he also uses a ZWO dual band filter for that one as well. Once again, the detail of that is very fantastic, absolutely brilliant. This is Ray again, and this is M13, Great Globular Cluster in Hercules. These are well, as it says, a globular cluster of stars, but very, very old stars out on the edge of the galaxy. Some people say they can see this naked eye in Hercules. I've never been able to, but a pair of binoculars, you can pick that up very, very easily, and the telescope starts to actually resolve the stars in there as well. Okay, so that's, Ray, is that 3 or 32 hours worth? I wouldn't say 3. 2 hours worth. I got it there now, yeah. And if you look down here as well, this sometimes gets overlooked when you're looking at M13. There's a little galaxy just to the side. Can't remember the number of it, but if you're looking at M13, try and find that galaxy as well. And then here's Ray's IC 1396, the Elephant Trunk Nebula. I can sometimes see this if I'm looking in the right angle, the elephant's trunk. It's down that way. Once again, Ray, absolutely stunning the way you brought all the colors and structure into that. Well done. I think this is the final one of Ray's. If you remember, I showed you the image of M27, the Dumbbell Nebula earlier, the one I took. Well, this is what Ray does. He is much more patient with the processing than what I am. I must learn a bit more patience with that. But once again, absolutely stunning image there. Absolutely, you know, the detail and structure in that is just, it blows me away, Ray. Well done. And so now it's over to Mick for the Moray Sky at Night. Thank you, everybody, for sending in those images. Keep them coming, please.
Cheers, Pete.
Okay, that's it, Mick. We got you.
Okay, doke. Happy New Year to you all, and welcome to the first of this year's Moray Sky at Night. So I'll start as usual with a run through what's happening with the planets. Excuse me, the moon and meteors, followed by a tour of the portion of the night sky, and I'll finish off with a word on comets. So the planets, our inner planet, Mercury, is coming to western elongation on the 12th of January. And you'll be able to see that in the morning, as I've got here on Stellarium showing you. Venus is bright, and that's not far from Mercury in the morning sky at a magnitude of -4. The Earth, which I don't often mention, We were at perihelion, which is the closest point to the sun in its yearly orbit, back on the 3rd of January at 3:39 in the morning. And that was at a distance of 0.9833 astronomical units, which is 147,100,081 kilometres. So Mars, the next planet out, that's in the same area as Venus and Mercury. And if I just remove the ground quickly to show you where it's at. So it's just following Mercury. So by the time that rises with the sun, it's going to be a bit washed out. If I just if I take a couple of hours forward, even before the sun's risen, you'll see if I put the atmosphere on, it's going to be washed out. So pretty much forget about Mars for the time being. Jupiter, let's go to the evening and have a look at where that's at. Down to the sun, zoom out a wee bit. There we go. So just after sunset here. Okay, so Jupiter, as you can see, is to the south, and that's in Aries. Put on some lines and names for you. Jupiter's in Aries. Excuse me, magnitude of minus 2.4 to 2.5 through the month. Saturn can be seen just after sunset, and that's at a magnitude of 1 in Aquarius. Uranus is across here, close to Jupiter-ish, and that's in Aries at a magnitude of 5.7. And Neptune is round about here. Oh, he's got it. At a magnitude of 7.9. That's in Pisces. So some possible photo opportunities for you through the month with the moon on its travels. If we go to 7. So dawn on the 6th through to the 8th, we'll see that the moon is approaching Venus. So that's just before sunrise. And you should be able to capture Mercury at the same time. Now, obviously be very aware of the rising sun and don't go pointing any cameras or any viewing aids, binoculars, etc. towards the sun and that when you're viewing this area, because it may well, and it probably will cause you permanent eye damage. So just be very careful of that. But that's a good opportunity there to catch them, although they are quite low. Going to the evening of the 8th, and if I swing round to the north, and round about, yep, just here. So even early in the evening, the quadranted meteor shower. So that started back on the 28th of December, and it continues right up till the 12th of January. It did peak already back on the evening of the 3rd into the 4th of January, but that's just to show you where the radiant is, so you can look out for that. Look out for some meteors above the horizon to the north. Through to the 12th, as I've already mentioned, I won't go back there actually. Mercury will be at its greatest western elongation. So that's at 14:37 in the afternoon, but you can catch that, as I said, at sunrise across to the south-southeast. On the 13th, I need to go in the evening now. Not going far enough, there we go. So the moon is at perigee, so that's I'll go and hide myself here. at 10:36, the moon's at perigee, so that's its closest distance to Earth. It'll be 362,266 kilometers. On the 14th, it'll be just 2 degrees to the north, to the south of Saturn. Moving to the 15th, it's going to be close by Neptune. We'll continue through the month, 17th, 18th, it's going to be right next to Jupiter. And on the 19th by Uranus, or Uranus. On the 20th, it'll be near the Pleiades. I think that's going to be, it's going to be a first quarter moon when it gets to Jupiter towards Uranus and then Pleiades, so pretty good photo opportunity there. The 19th, 20th, continuing. Let me zoom out a wee bit. So to 24th, it'll be by Castor and Pollux, the head of the twins of Gemini. I'll take the time forward a wee bit. 8 o'clock at night. Down on the 27th, it's going to be by Regulus once Leo has risen. So that is the planets. So next I'm going to do is give you, especially for those new, give you a little few pointers, just get rid of some of this things. Okay, so what I'm going to do is I'm going to go through the big G of the winter night sky, which was provided to us by Bill Leslie. So this is a great way to find your way around the winter sky. And on the way, you'll find out about some of the dominant constellations at this time of the year and the names of some of the brightest stars. So looking to the south, it has to be around about 7, 8 o'clock at night, maybe even before. If you've got a good view, you'll be able to see easily the belt of Orion. So follow these up about 30 degrees and you'll find the bright orange star Aldebaran, which sits in the V of the Hyades, which are part of Taurus. The Hyades is not actually part of the Hyades because it's not at the same distance, but that's where it's at. So that's the start of this big G. Let's zoom out a wee bit, right, and then so we go up about 20 degrees, almost directly north, we find the brilliant Capella, which sits in Auriga. And then following round to start making this G, we'll find Castor and then Pollux, which are the heads of the twins of Gemini. And down to quite a barren part of sky, you find this bright star Procyon, which is part of Canis Minor. And then the brightest star in the sky at the bottom, Sirius, the dog star, in Canis Major. And as we head back up, just take these away just to see what it'll look like. You find Rigel at the foot of Orion. And if we come up to the next star up on Orion, we will find Bellatrix and then across to Betelgeuse. Betelgeuse, a red supergiant. It's so enormous, if it replaced our sun, it would reach right past Mercury, Venus, Earth, Mars, and almost out to Jupiter. It's that big, absolutely enormous. So that's the big G. I'll put constellations on now and leave them there, I think. So going up from Betelgeuse through Capella, it's quite another barren part of sky. We find Camelopardalis. Stellium's kindly just going to spin for me because it's near the pole. And one of the best asterisms though in this constellation is known as Kemble's Cascade. So it's a line of faintish stars covering a distance of around 3 degrees. So it's a great treat using large binoculars. And the stars are colourful too, which makes it really interesting and nice for anyone imaging. It was named by the legendary American amateur astronomer Walter Scott Houston in honour of his friend Lucien Kemble, who described it to him. And it tips into the bright open cluster NGC 1502, which might be when you're looking for Kemble's Cascade, it might be one of the most obvious bar this star. It's just here, the Jolly Roger cluster. And that's a compact 7 arc-minutes in diameter. Just over a degree to the north, we also have NGC 1501, a very enjoyable planetary nebula. It's nicknamed the Oyster Nebula, maybe because of its 14th magnitude central pearl. And despite an off-putting magnitude of 13, it's quite an easy bluish disk, and it's quite a respectable size as well. It's similar to Jupiter in its apparent size. So heading to the north, we find Polaris, which I mentioned, sits in Ursa Minor, the little bear. And across the other side of the sky, of course, a lot of you probably recognise, take these lines away, you recognise the plough. So an easy way to find Polaris is if you use these two stars in the plough and just follow them directly up to the next brightest star, and that's you got Polaris, or the pole star, the North Star. An important star for us in amateur astronomy because we use it to align our telescope mounts, which is something you really need if you're doing long exposure astrophotography. So in here we have a couple of galaxies that are quite interesting. M81, M82, Bode's galaxies. To find this, what we do is use these two stars, this one here, through Dubhe, and out about the same distance, so about here, shouldn't find them, oh, I've gone too far. So here we have M81, lovely spiral galaxy, and we are right next to it, we have M82, the cigar galaxy. There's another, what was it? Right, there's another fine galaxy, NGC 2403, which in my notes is between the heads of the Great Bear and the Lynx. So the Great Bear, Ursa Major, and we have Lynx next to it. I'll stick some artwork up, you can see where the heads are at. So this star here that's at the head of the Lynx, if we go roughly halfway, should hopefully find in here. I'll just put them off on there we go. NGC 2403. It should be pretty easy to see this through some large binoculars. It was initially thought to be part of the M81 group, and it's around 9 million light years away. I don't know why stellarium, I did check this and I think it's about 8.5 million light years, but stellarium's got it down as 13.7. I think they need to get their act together at stellarium. A lot of things are a bit wrong. Anywho, so now we're going to head up to Cassiopeia. Just take some of this letters and stuff out of the way first. So Cassiopeia is pretty easy to find. If you find that pole star or not, or even the plough, if you find the plough, and head up through the pole star, and then look roughly same distance the other side of the sky, you find this group of stars here, which now I'm going to change the time, be a bit odd. I'm going to go to 10 in the morning because I found out that makes it the right way, kind of the right way up. Oh, actually on the 27th, that's not right, I'll go to the 15th. Right, there we go, makes it the right way up. So, big W, Cassiopeia, put the lines on, there we go. And there's plenty to see around Cassiopeia, especially open clusters and things. You can see, if I zoom out a little bit, you see this milky band. This is the Milky Way that we're looking through the disk of the Milky Way. So you've got all that. This milky part, incidentally, is just dust and debris, stopping you focusing on a lot of the brighter stars. But there's plenty to see in here. So the first thing we're going to find is Messier 52. So using these two stars to the right of the W, if we follow them through about the same distance, about here, I'll cheat, I'll use the thing, there we go, it's there. We have the Cassiopeia salt and pepper cluster, M52. If we go back to CAF, this one, and then find, oh, then we want to find Rho Cassiopeia, and then Omicron Cassiopeia is this one here. So somewhere in between, we have NGC 7789, Caroline's Rose Cluster, named after Caroline Herschel, sister to William Herschel. And this large jewel brooch is quite rightly a favourite. Next, we're going to go to NGC 103, which lies close to Rochba, around here. And this is easy to see even with binoculars, and it appears as a nebulous fan-shaped patch. We also have the Dragonfly cluster on the other side from Rochba, NGC 457. And as you can see, Stellarium has thrown up a whole load of things here. We also have NGC 663, the Lawnmower cluster. A bit like Pete's monkey earlier. I'm sure if you squint the right way, it looks like a lawnmower. No idea. And we have the Fuzzy Butterfly cluster, NGC 654. Of course, for most of us, me included, let's go back to the evening before I get any further. One of the most interesting things to look at is Orion, and this is quite an easy challenge for this month. Object challenge Messier 78, a reflection nebula. So back to this belt of Orion, if we use the left-hand star Alnitak and go up about 2 degrees and across to the east 1.5 degrees, just here. I always get the wrong one here. That is the right one, but I don't know why it's put. Give me 2 seconds. Let's get the right Stellarium button. There we go. Casper the Friendly Ghost Nebula. So that's your challenge this month. I want to see all your pictures next month on this. It's got an apparent magnitude of 8.3 and it's a distance of 1600 light years from Earth. It can easily be seen in large binoculars and small telescopes, and they show a hazy comet-like patch of light with 2 10th magnitude stars that illuminate it. It's also visible in 10 by 50s, 10 by 50 binoculars, that is, as a dim patch, but that does require a clear dark sky to be seen. Finally, I'm going to just quickly, I've already put in a newsletter about comets, but I just wanted to show, you quickly, if you use Stellarium, how you can find the comets. Now, you have to go and download them. If anybody needs any information, what I'll do is I'll put that in. I'll maybe ping that out in an email actually, because I've got some notes here how to add them to Stellarium, because they might not just appear on it. But anyway, to get a diagram or a trail of where they are, called an ephemeris, if you go to this astronomical calculations button here, ephemeris, now the two that are on my list, 12p Pons Brooks and 29p, yeah, so I've got these two here already from earlier on. What I'll do is you just select some dates. So I'll go to today and the end of Feb, calculate, and then close that, and then go and see where Stellarium's drew them. Now I just happen to know that the first one is to the northwest. So here it draws you a nice line of where they're going. And I'd already selected things on the buttons in there, so 10-day intervals. So this is today, so the 5th of January, you can see here, and that's the magnitude. It's actually, the latest observed magnitude I found on the 2nd of January was 9.5. But this is going to, over the next couple of months, get slowly brighter. I won't go into any information because it's already in the newsletter, but that's just to show you how you can find them. And the other one is round to the east. There we go. I have to zoom in a bit here. And that's, as you see, heading away from Cancer. So this is today, 5th of January. Stellarium. There we go. That's heading that way, but this is quite dim. You're going to need quite a substantial telescope, I think, on this one. Maybe a small telescope will work. I'm not sure. I've not had a chance to have a go myself. I won't bother going into the other two that I've put on there, but it was just to quickly show anybody who wants to know how to draw the lines for the comets. But I'll ping out an email to everybody just showing you how you can add the comets, unless you want to go and watch it on the YouTube channel, of course, which I recorded quite a while back. That's me.
Okay, Mick, thank you very much. Great again, some good things to see if the skies ever clear up.
Yeah.
I'm going to touch on that in a minute, actually. So we've just got a bit of club news to finish off with. Won't take very long, and we're near enough on time tonight, which is good. Yeah, don't forget, being part of Sigma is not just about these sort of monthly meetings. We have got telescopes for hire. We've got 3.5-inch refractor, and also Skywatcher 6-inch Dobsonian. To say we do charge a small fee, which can be waived if people are having problems. Just a small fee of £5 to cover any damage that might happen to them. And you can charge, and you can borrow them for a month at a time. At the minute, they're just sort of gathering a bit of dust. It'd be nice if some members out there, if anyone's not got a telescope, to come along and hire it. You won't be able to have it possibly until February now. So we got plans for an outreach thing, which I'll tell you about next. Yeah, so outreach has been fairly quiet at the moment, but I had a request today from the Historic Wheels Club to do a talk for them, or observing hopefully, but talk probably if the weather doesn't clear up. To say we've just been stuck under these Atlantic lows now for what seems to be about sort of 4 or 5 months, if not longer. But hopefully the weather pattern is changing now, and very soon we'll get some high weather, some high pressures and some clear weather, and that will allow us to I know what I was going to say, but any area, any sort of outreach at all. If there's any other clubs out there that's wanting to talk, or if we can do arrange an observing session for you, then please let us know, and we will do. Observing nights, yeah, as I say, it's just been terrible. I think probably 4 or 5 nights we've had the chance of doing it, but then it's the clouds have come over within an hour, so it's not really worth getting us all out for a set the telescopes up just for an hour. So we'll keep an eye on it though, and the observing group will actually, as I say, keep an eye on the weather, and we'll try to get out there and do some observing as soon as we can. Don't forget also, we've got the observatory now that, as I say, as part of the Sigma membership, you can come and use the 132mm Williams Optics telescope in the 2.7 meter dome. And I say, once again, we do charge a little bit for that, which is just £2 per person per night. So once again, just to cover any incidentals that happen, or any repairs that may be needed in the future. So there is a little bit of training needed for that. That's all in the newsletter. And say, don't be scared of it. The training only takes 15 minutes. It's just to show you how to use the telescope and how to open the dome. So say, you get all this just for your £28 a year membership. The one thing I was going to mention is that we've got a plan of sending out a little survey to all the members, just to see if they're happy with how the meetings are going, and if there's sort of anything else we're doing right or wrong. Tim and Helen are working on that at the moment, and once it's together, I think we'll be sending it out fairly soon. Okay. And the next thing, don't forget to invite a friend. If you've got any friends who are interested in astronomy, just let them know. Our next few meetings are online, next 2 at least. So if you've got any friends, just get them to email Mick, and then Mick will send out the Zoom links to them. But obviously, if you do become a member, then you will be kept up to speed with all the events that we've got going on, all the observing sessions, the observatory opening times. So we do all that on Spond and WhatsApp, and you'll get the newsletter every month, and you also get Mick's Sky Guide as a PDF come through every month as well. So plenty that you get for your membership fee. Don't forget, if there's anything that you would like to say to us, well, say to me especially, but if there's anything you think we're doing right or doing wrong, I'll take that, and I'll take the emails of the thank you. Or if there's anything else you think we could be doing, just let us know. Pop me an email, and then we can get that done for you. So yeah, so with that, I want to thank Andy for his wonderful talk. I want to thank all the first-time visitors as well that come along. Hope you enjoyed the evening, and don't forget, just contact Mick if you want more information about next month. Chris for doing the Q&A, and Rich for the vote of thanks. Mick for your Morning Sky at night, and all you members out there are sending their photographs in. Absolutely brilliant. Took me a while to get them put together there and sorted out, but just keep them coming. Please do keep them coming, especially if this sky clears up and gives us a chance to get some more. So I think that's about it from me. So with that, I'll say good night. Thank you all for coming along. Andy, again, thank you very much, and we will see you under a starry sky sometime, hopefully. Good night, everybody.